Or before they look back. Actually, those would be better.
And I
Not on use it. This only works for integration as part. So which one to choose? Would be like no, it wouldn't be X-ray, it would be So far, I haven't seen it up one time.
Just got the knack.
They told me this acronym in that class for selecting which part you use in substitution.
Oh yeah, what is it?
Liate, L-I-A-T-E.
L-I-A-T-E?
Yeah.
What does that stand for?
L stands for log, I stands for trig, A stands for algebra, T stands for trig.
L stands for, did you say long?
Log.
Logs. Uh-huh.
And E stands for exponent. And I've used it on homework and haven't had an issue on.
And what does T stand for?
Trig.
Trig, algebra, inverses, and exponents. Mm-hmm. So it's L-I-A-T-E.
Yeah.
Interesting. It's to help you choose which functions to choose as your U for integration by parts. So once we get started here, I'll put that on here. In fact, we are starting right now. So did you have a question, Jenna?
No.
Okay. So first of all, I want to remind everybody that the homework number 4 is due this Friday. And there are a couple of things that I want to do before we get back onto section 7.3 about trig substitutions. One of them is an acronym that I just heard was given, LIATE, and this involves integration by parts. And it's an acronym apparently to help you choose what is to be your U with integration by parts. So this L here stands for log functions. The I here stands for inverse functions. The A stands for algebra, but I assume by that they're talking about polynomials. Is that correct?
Well, all I'd use it for is like there's just X or something.
That's polynomial, right? That's a polynomial. Mm-hmm. The T stands for trig functions, and the E stands for exponent functions. So the name itself isn't very catchy, LIATE, but anyway, it can perhaps give you a help in what to pick for the U. Okay, all right. Okay, the other thing that I wanted to go over, first of all, is just something about some very basic U substitutions that I want you guys to be able to do without having to formally do a U substitution. So this is what I'm talking about. If A is some number that doesn't equal 0, and we want to get the antiderivative of the E taken to the AX power, just get it in your mind that the antiderivative is going to be 1 over that number that's by the X times E to the AX plus the C, without having to formally do a U substitution on this. Similarly, looking at, say, the sine of A times X dx, getting its antiderivative, again, we're going to do the 1 over A, 1 over the number in front of the X, and of course, let's see, for the sine, the derivative of the negative cosine is the sine, so it'll be minus 1 over A cosine of AX plus C. And finally, for the antiderivative of the cosine times a number AX, then again, we have the 1 over A in front, and then this time the antiderivative function is the sine of AX plus the C. It just will make your life go a little bit, things go a little bit faster when you're doing problems if you don't have to bother with a formal U substitution for getting these types of antiderivatives. Does anybody have any question on just these formulas? If you work it out, if you check by getting the derivative of these, by using the chain rule, you will come back to those functions. Okay? All right. So let's get back here then to section 7.3, and we're doing here trig substitutions to evaluate integrals. And let me write this table up here again that we will be using. Okay, if the expression in the integral is some number a squared minus x squared under the radical, then the substitution we do is we let x equal a, the number a, times the sine of theta, where theta is between minus pi over 2 and pi over 2. All right. And then the identity that's involved with this substitution is 1 minus the sine squared of theta equals the cosine squared of theta. All right, so that's the first one. So again, I want to point out here that the x is after the minus. And we end up using a times the sine. Now the second one then is where we have a plus sign. Well, this is rapidly deteriorating. Plus sign, a squared plus x squared. So we have a plus. What we do with our substitution is let x equal a times the tan of theta. And here we're talking about anywhere in the first and second quadrants, theta between minus pi over 2 and pi over 2. And the identity that we use with this is 1 plus the tangent squared of theta is equal to the secant squared of theta. And then the last one in our table is where the x squared comes before the minus sign, x squared minus a squared under the radical. So here is the x is in front of the minus, and we use a secant. So x, we let x be replaced by a times the secant of theta. And now this time the theta is in the first and third quadrant. It's between, let's see, theta between 0 and pi over 2, and between pi and 3 pi over 2, first and third quadrants. And the identity that we're going to use, that we use here, is the secant squared of theta minus 1 is equal to the tangent squared of theta. Okay. All right. All right. So those are our tools that we're going to use here. So we're going to just do some examples here to see how this works. All right. So we did 2 examples in the last class. So let's see what we have here. Now we're going to do the antiderivative of 1 over x squared times the square root of x squared plus 4 dx. So notice we have a plus here, so we're going to use the tangent. And so our a is equal to the number 2, because 4 is 2 squared. So a is equal to the number 2. So we let x equal 2 times the tangent of theta. That's our substitution. All right. Let's go from there. Our dx then is going to be, well, what's the derivative of the tangent? That's the secant squared. So it's going to be 2 times the secant squared of theta d theta. All right. Now what is this whole radical going to be replaced by? The square root of x squared plus 4 is going to be replaced by, well, when I square x, I have 4 times the tangent squared of theta, and then the plus 4 gets replaced by the plus 4. And notice we can take a 4 out from each of the terms. Now, when I take a 4 out from the radical, I have a 2 in front of the radical. And then under the radical, I'm just going to have tangent squared of theta plus 1. Okay? And then we know that 1 plus the tangent squared of theta is the secant squared of theta. So that gets replaced like that. And then because this is in the first and fourth quadrant, this is going to be positive. So I can just replace this, the square root of secant squared, I can just replace it with the secant. So that whole radical then gets replaced by 2 times the secant of theta. All right. All right, so let's go back here and do the rest of our substitutions here then. We have dx is going to be 2 secant squared theta d theta. Notice, don't forget, we have an x squared in the denominator, so I've got to replace it by the x with 2 tan of theta. So x squared gets replaced by 4 tangent squared of theta, squaring it. And then I replace my radical by what I just found it was equal to, times 2 times the secant of theta. Okay, we've replaced everything. Now let's cancel out what we can cancel out. All right, I can cancel out a secant from top and bottom, and I can cancel out a 2. So what I'm left here with then on top is just the secant of theta d theta. And down below, oh, actually, I cancel out the 2 here, 2 here, secant, and I'm still left, though, with the 4 down below times the tangent squared of theta. All right. So now I've got this, and then this is one of the tricks you need to be able to know what to do with. So you say, well, what do I do now with this thing? Because there isn't any immediate substitution that comes to mind here with this. What you want to do with this is convert everything to sine and cosine and say a prayer that things will work out. All right? That's what we want to do. So the secant is 1 over the cosine. So I'm going to replace this by 1 over the cosine of theta. And then the tangent squared times 4, this is all in the denominator. The tangent squared, the tangent is sine over the cosine, so this is sine squared over cosine squared, and then I have my d theta. So I've got a bunch of stuff in the denominator. Let me simplify further. If I have a fraction in the denominator, I can get rid of it by doing the reciprocal. So this thing now becomes 1 over, let me write the 4 first, 1 over 4 cosine of theta. And then this fraction, sine squared over cosine squared in the denominator, can become the flip of that, cosine squared of theta over sine squared of theta, where it's no longer considered in the denominator, d theta. All right, basic algebra manipulation. And now let's see if there's something more we can cancel out. And there is. Notice we have a cosine on the top and bottom, so I can cancel out a cosine. So this is 1 over 4. I'm canceling out that cosine, sine squared of theta. And then on top, I'm only going to have 1 cosine d theta. All right. And now we look at this and hope for the best, and we can do a u substitution with this one. What are we going to select as our u here for this? Well, you only have 2 choices. The sine. You can select the sine for our u. Let u equal the sine of theta. So therefore, our du is going to be the cosine of theta d theta. All right. And that's going to work out. So I replace that numerator, cosine of theta d theta, by du. I have the 1 over 4 here. And then I have, instead of sine squared, I'm going to write u squared. All right, I can do this antiderivative. This is 1/4 times u to the negative 2 power, just rewriting it with the exponent. And do the antiderivative. I'm going to get 1/4 times u to the negative 1 divided by negative 1 plus capital C. Or, a little nicer way to write this is to put the minus out front. 1 over 4, and then put the, let's then replace the, let's put the u in the denominator. We'll flip it back into the denominator, plus c. And then finally, let's replace the u by what it's equal to. So I get minus 1 over 4. Now the u was sine theta, plus c. All right. Okay. Now the thing is, all right, is there another way I can write that last thing, minus 1 over 4 sine theta, using a trig function? Cosecant is the reciprocal. So another way I can write this is minus 1/4 the cosecant of theta plus c. Now the thing is, way back up here, our integral has the variable x. Way down here, after we had done our trig substitution, our antiderivative has the variable theta. We need to get our answer in terms of x. So let me go over to this side here. Need to get answer in terms of x. Okay, this is where we draw a picture. Let's remember initially that x is equal to 2 tangent of theta. So let me divide by 2, and so we have tangent of theta is equal to x over 2. So let's draw a triangle to reflect that. So a right triangle. Let's fill in our angle theta right there. And its tangent is x over 2. So the tangent is the opposite over the adjacent, like that. So we just label the dimensions of those two sides of the triangle. And then we want to fill in our hypotenuse here using the Pythagorean theorem. So this is going to be, the hypotenuse is going to be the square root of x squared plus 2 squared. All right. So we have our picture here all in terms of x. So now let's go with what our antiderivative is. It's minus 1/4 times the cosecant. So from this picture here, we can see that the cosecant, let's see, the cosecant in my mind, I remember, is 1 over the sine, right? So therefore, so 1 over the sine is going to be the hypotenuse over the opposite. So the cosecant in terms of x is x square root of x squared plus 4 divided by x. So I can then just fill in my final answer. It's minus 1/4 times the square root of x squared plus 4 over x plus capital C. And that is my final answer then with this.
Where did you get the denominator?
Where did I get this denominator x? Because our antiderivative is the minus 1/4 of the cosecant. So the cosecant is the hypotenuse over the opposite. All right, it's the reciprocal of the sine. So that's where the x, which I had put into my picture previously, is the opposite side. So that's why it goes down in the denominator there. All right? Okay. All right. Question on this one. We're going to do another one, very similar, except now this one is going to involve the other third formula in our table. So this example is the antiderivative of dx over the square root of x squared minus 25. All right. So notice here we have I'll just put this, we have the x in front of the minus. So we're going to use the secant formula. Now, our number here is 25. This is a squared. So a is just equal to the number 5. So our substitution is x equals a times the secant of theta, but a is equal to 5, so it's x equal to 5 times the secant of theta. Okay? All right. Now let's get our dx. Okay, the derivative of the secant is the tangent. So this is 5 times the secant of theta, tangent of theta, d theta. All right? And let's figure out what that radical looks like. So the square root of x squared minus 25 is going to be replaced by the square root of, let's see, 25 secant squared of theta, that's our x squared, minus 25. And so I have that 25. I'm going to take that out from under the radical as a 5. And so this is 5 times the radical secant squared of theta minus 1. And secant squared of theta minus 1, this thing right here, is the tangent squared of theta. So the square root of the tangent squared, it's going to be 5 times the tangent of theta is going to be what our radical equals. We okay with that? Substitution. So let's see what our new integral looks like then. dx, I'm going to replace with 5 secant of theta, tan theta, d theta, all over, and then my radical is being replaced by 5 tan of theta. Okay. This one doesn't require as much manipulation. Notice right away I've got a tan theta that'll cancel out, and the 5's will cancel out. So what I'm left with then is the integral of secant of theta d theta. Now this is a formula that you guys are all going to know by the next test, is this antiderivative of the secant is the natural log of the absolute value of the secant of theta plus the tangent of theta, close the absolute value, plus the c. All right. Okay. So we have now obtained our antiderivative, but it's in terms of theta. So therefore, we need to get x in the picture. Get x in our answer. And for that, I'm going to draw a picture again. So let's draw the triangle. Let's put in our theta. Now let's go up to the beginning here, that x is equal to 5 times the secant of theta. That's our original substitution. So if I divide by 5, I get secant of theta is equal to x over 5. Now let's see, the secant is the opposite of the cosine, so it's the hypotenuse over the adjacent. So I'm going to label x as my hypotenuse, and 5 for the leg right by the theta. And then this other leg, I'm going to fill in again using the Pythagorean theorem. This is going to be the square root of x squared minus 25. Okay, so now we just had, so what's our answer here? Okay, it's the, let's see, let's figure out, well, the secant of theta, that's already, we already know what the secant of theta is. That's from our original substitution directly. That's x over 5. So we're going to have the natural log of the absolute value. The secant of theta is going to be replaced by x over 5. Now, what's the tangent of theta going to be replaced by? The tangent is the opposite over the adjacent. So the tangent is going to be the square root of x squared minus 25. That's the opposite all over the adjacent leg, which is 5. Yeah, Jenna. Oh, no. Are you saying, okay, where I get cat. Okay, and you're not saying this, are you? That the square root of x squared minus 25 can be replaced by x minus 5? No, never. Never, ever, ever. You can't do that under a radical, break things apart like that. In other words, I can't do something like, say, the square root of 49 minus 25. I cannot say that that's the square root of 49 minus the square root of 25. This I cannot do. 7 minus 5. Oh, so I figured out from this inaccurate algebra, I have figured out that the square root of 49 minus 25 is equal to 2. Well, what's 49 minus 25? It's 24, isn't it? So I've determined through my own brand of mathematics that the square root of 24 is equal to 2. So I hope that convinces you never, ever to do that. I'm sure you'll remember. Okay. All right. I'm channeling my third grade Dominican nun teacher just now. But never mind. Forget that. Okay. So we've gotten so here is, let me close the absolute value. So we've obtained, in terms of x, our antiderivative. Now let's suppose that we're going to take the same thing in the integral, but this time I'm going to make it a definite integral. So let's suppose we had a definite integral instead. All right. So let's say our definite integral was, the lower limit was 10 divided by the square root of 3, and the upper limit was 10. And we have the same integrand that we did before, dx over the square root of x squared minus 25. All right? Okay, so I'm certainly not going to repeat the whole process of how we obtained the antiderivative. Let's write down what we got here for this. We got that our antiderivative, well, actually I do need to do something here. But I do have to repeat something, I'm afraid. Remember that we did this, x equals 5 secant of theta was our substitution. Now, since we are now, we're going from x to theta. We're changing from x to theta for our variables. So I have to change the limit of integration. Change the limit. All right? So let's see what we get here with the limits here. Now, the lower limit is x equals 10 over the square root of 3. Now, that is equal to 5 times the secant of theta. So that's my substitution right here. So now I need to find out what theta solves this. Well, let's divide by 5 rather, and I get 2 divided by the square root of 3 is equal to the secant of theta. And now we look at one of our special triangles that we looked at in trig, and this will be that 60, 30, 90 degree triangle, 60, 30, 90, where this is 1, this is 2 on the hypotenuse, and that's the square root of 3. All right, so what angle here gives me a secant of 2 over the square root of 3? Question to you guys. 30 does, yeah. Remember, the secant is the opposite of the cosine, so therefore it's going to be the hypotenuse over the adjacent. So theta here is equal to the 30 degrees, but I don't want to use 30 degrees. I want to use the radian measure, which is pi over 6. So when I change my limits of integration, my lower limit is going to be pi over 6, or 30 degrees. Now let's figure out that upper limit of integration. It was when x is equal to 10. We set that equal to our substitution of 5 secant of theta, and we divide by 5. We get 2 is equal to the secant of theta. All right, so what angle will give us the secant equal to 2? No. Pi over 2? Yeah. Let's look at our triangle. We've got the triangle right here. Here. Triangle. Yeah, 60 degrees. This angle right here, 60 degrees, or pi over 3, its secant is 2 over 1, the opposite of the cosine. So therefore, this theta is 60 degrees. Get used to drawing these special triangles. and 60 degrees is pi over 3. So my limits have now become pi over 6 to pi over 3. Now, earlier then, so we had found out that this substituted everything simplified in the integrand to secant, and so we got the antiderivative as the ln of the secant of theta plus the tan theta in absolute value. We don't put the plus c in because we're doing a definite integral. Now, I want to impress this on you guys. Since I'm doing a definite integral, if I've changed my limits of integration with my new variable, I don't have to go back to my old variable. Just keep it like this to evaluate the definite integral. Pi over 6 on the bottom, pi over 3 on top. Because there are some of you in the other classes too in here that want to confuse the two. If you go back to your original variable x, if I do all the substitution and go back to x, then I would have to use my limits would have to be the 10 over square root of 3 and the 10. But if I stick with my antiderivative in the terms of theta, I want to keep my new limits of integration with terms of theta. Does everybody get that? This is only with definite integrals. Alex, all right with this? Okay, all right. Okay, so let's just figure out what we get here. Okay, so we fill in the top number. We have the ln. Now, let's figure out what's the secant of pi over 3. Okay, just look at our special triangle. So this would be the secant of pi over, let me write these in. Secant of pi over 3 plus the tangent of pi over 3. Let's close that absolute value. Then it's minus the ln of the lower one, secant of pi over 6 plus the tangent of pi over 6. All right. And let's figure out what we get here. All right. Secant of pi over 3 is going to be 2 over 1. So this is the ln of 2 over 1, plus, now the tangent of 60 degrees is the square root of 3 over 1, so that's plus the square root of 3. Now I don't even need the absolute value here, because those are both positive numbers. Minus the ln. Now we have to look at the other angle, the pi over 6 or 30-degree angle. So now this is our reference point here. The secant of this is going to be 2 over the square root of 3. So minus the ln of 2 over the square root of 3 plus, and now let's look at the tangent of the 30 degrees. That's going to be opposite over adjacent 1 over the square root of 3, plus 1 over the square root of 3, like that. Okay. So we don't have to go back to our original limits of integration for the definite integrals, because we're just figuring out a number that it's equal to. All right. Question on that?
Do we have to take, like, I know in my last class we had to keep a root on the bottom.
We had to keep a what on the bottom? Oh, I'm not worried about that. That whole business about rationalizing the denominator, where if you have a square root of 3 on the bottom, oh my God, you've got a square root of 3 in the denominator. I don't care. All right? No big deal to me. All right, I want to do another example here. This one is also going to involve the secant. And here it is, antiderivative of the square root of 9 minus 4x squared. I'm sorry, this will involve the sign. I misspoke. Notice we have the x is after the minus, so we're going to use a sign. 9 minus 4 times x squared. All right, now this one needs a little bit of work here to figure this out. What we're wanting is we want something like the square root of a squared minus, let's just say u squared. All right, that's in our table, that's what the first column of the table, that's what they look like, all right? But what we have here is 9 minus 4x squared instead of just a number squared minus the variable squared. So there's something we can do here with this to get it like this. Let's divide by 4 inside the integral to make that 4 a 1. But if we divide inside the radical by 4, we have to multiply outside the radical by 2. Does everybody understand that? If we divide by 4 inside, we have to multiply outside by 2. Otherwise, we're changing the expression. All right, so this is going to change to, all right, I'm dividing by 4 inside. So this is 9, underneath, it's 9 over 4 minus x squared. But I then have to counteract that by multiplying by 2 in front, like that, dx. So this is what I'm saying here. If we divide by 4 inside the radical, or under the radical, we must multiply by 2 outside the radical. All right. Now I've got it in this form here of a squared minus x squared, all right, which is what we see in our table. Except this time around, my a squared is equal to a fraction 9 over 4. But notice that in this case it's nice because they're both perfect squares. So what would be my a if a squared is 9 over 4? 3 over 2, right. All right, so this is going to be my substitution then. I use a sign, so I let x equal, it's a times sine of theta, but a here is now 3/2, so let x equal 3/2 times the sine of theta. That is my substitution. So I had to do a little bit of work here to obtain that substitution. Let me put a square around this. All right, so let's get our dx and all that. So dx is 3/2 times the cosine of theta, d theta, all right? And then let's see what our radical becomes here. Our new radical is the square root of 9/4 minus x squared. Well, let's replace the x with the 3/2 sign. So this becomes the square root of 9/4 minus 9 over 4 sine squared of theta. And notice we can take a 9/4 out from under the radical, but what would I have to put in front to do that? 3 over 2 if I take that 9/4 out. So this becomes 3/2 times 1 minus the sine squared of theta, and that's, of course, the cosine squared. So this becomes 3/2 times the cosine of theta when I do the square root. So that's what my radical is going to be replaced by that. All right, so let's go back to our original integral then and I should have put a dx up here and I didn't, and see what we get here. So I'm going to, now, actually I'm going to go with how I had rewritten it right here. So I have a 2 here, and then I'm replacing that radical with what I had just gotten, 3 over 2 times the cosine of theta. And then I have to replace my dx. So my dx, I got, let's go up here, I got a 3/2 times the cosine of theta d theta. All right. So I replaced everything. And let's do some simplifying here. Well, a 2 cancels out. So let's see, what am I left with? I'm left with a 3 times 3, 9, and then I still have a 2 down there. And now I have a cosine times a cosine. That's a cosine squared of theta, d theta. And I want to get that antiderivative. Well, this is where we have a couple of formulas. We have a formula for the cosine squared. Remember that the cosine squared of theta can be replaced by 1/2 times 1 plus the cosine of 2 theta. So that's what I'm going to do here so that I can get an antiderivative. So I'm going to do that replacement. So I have 9/2 times, now let me replace the cosine squared, so that's replaced by 1/2 times 1 plus the cosine of 2 theta d theta. All right. Okay, so we can certainly distribute. Let's go on and do that. I have 9 over 2 times 1/2, that's 9/4 times 1. So that's my first term. Plus, and then again, 9 over 4 times my second term of cosine of 2 theta. All right, so I've just split it up like that. And both of these terms I can get the antiderivative of. The 9/4 is going to be replaced by 9/4 times my variable theta. Now, the cosine, and then I have a 9/4 here. And then I'm going to use the basic quick substitution here that I mentioned at the very beginning of class. For the antiderivative of the cosine of 2 theta, I make it as a 1 over 2, because that's my number there. And then we know the antiderivative of the cosine is the sine. So I'm replacing cosine of 2 theta with its antiderivative 1/2 times the sine of 2 theta. Okay. All right, and then that's plus c. Okay. Well, and we're still going to have to do some work with that, but let's realize, okay, we need to get x in our answer. So let's draw a picture. Again, another right triangle, and we stick in theta. Now let's see, from way back up here, we had that x is equal to 3/2 sine of theta. All right. So that's the same as, if I multiply both sides by the reciprocal, that's the same as 2/3 x is equal to the sine of theta. Just multiplying it by 2/3. Okay, so we have a numerator of 2 times x and a denominator of 3. This is the sine. So the sine is the opposite, which will be the 2x over there, over the hypotenuse. My 3 is going to be up there. And then I can fill in my other leg by doing the Pythagorean theorem, and that'll be the square root of 9 minus 4x squared, like that.
Will using the Pythagorean theorem always result in what you pretty much started with at the end?
Right. Okay, because notice that, gee, that looks very familiar, doesn't it? That square root of 9 minus 4x squared, isn't that what we started with? Yeah. All right, so now let's use that then as our template here. So we have, first of all, we have 9/4 theta. Now, what can I, now we know that the sine of theta is equal to 2x over 3. So what will I replace theta by? By the sine inverse of what then? The 2x over 3, right there. That's what my theta is going to be replaced by. Now we've got a little bit of a problem here. Notice that this other formula here, it involves the sine of 2 theta. And my triangle is only for this angle of theta. So I need to use yet another one of the trig identities that you guys are all going to know, is for what's the sine of 2 theta equal to in terms of just theta? Yeah, I just remembered it as 2 sin cos. 2 sine theta cosine theta. So let's go up here, and this sine of 2 theta up here, this right there is going to be replaced by 2 sine theta cosine theta, right there. That gives us our nice single angle. So let's cancel out. We have a 2 on top. Let's cancel out a 2. So this second term in our antiderivative, then it's just going to be 9 over 4 times the sine of theta cosine of theta. Cancel out a 2. Okay? And we can use that because we can get the sine and cosine from our picture. So let's go down below here. So plus 9/4. Now we need the sine of theta from our picture. Well, we know the sine of theta is 2x over 3 times, and then we need the cosine of theta, and that's going to be adjacent over the hypotenuse, square root of 9 minus 4x squared, also over 3. And then we have plus c, let's not forget that. So this whole thing right here is our antiderivative in terms of x. Of course, there's little simplifications I can do here. I have 3 times 3. That'll cancel out a 9. 2, I can take a 2 out and simplify that second term a little bit. But in essence, that's what we have. Okay. Now, I want to finish this up and then we'll take a quick break. Just like with the previous problem, what if our original integral was a definite one? What if the original integral was a definite integral? All right. So therefore, let's suppose it was something like this. From 0 to 3 over 4 to 3/4 of the square root of 9 minus 4x squared dx. Okay. We know the substitution that we had done. We had done that x is equal to 3/2 sine of theta. So we can just get things now in terms of theta, but we have to change our limits of integration. Change the limits of integration. Okay, so first of all, x is 0. So if x is 0, we have what? 0 is equal to 3/2 sine of theta. So what would be the angle theta if its sine is equal to a 0? The sine of what angle equals 0? 0, right. So theta equals 0. So that's our lower limit of integration. It's also a 0. Now we also have, if x is equal to 3/4, then we have 3/4 is equal to 3/2 sine of theta. I'm just replacing the x there by 3/4. Okay, well, let's multiply both sides by the reciprocal 2/3. So we have 2/3 times 3/4 is equal to the sine of our theta. And then that left-hand side simplifies to 1/2. Okay, so what angle has the sine of 1/2? Yeah, pi over 6. Let's draw. Yeah, don't feel bad. I always have to draw the triangle. It's like I'm too visual or something. I gotta draw it. 1, 2, square root of 3. We see that for the sine, for 1/2 being the sine, that has to be our 30-degree angle for the opposite over the hypotenuse. So theta then is pi over 6, 30 degrees. So our upper limit is pi over 6, okay? Now we found out, and of course, if we were doing this for the first time, we would have gone through the whole process before. We found out that our integral that we got is 9/4 times 1 plus the cosine of 2 theta, d theta, from doing all the simplification. And we found that its antiderivative then, I don't want to repeat this process, is going to be 9/4 plus 9/4 times 1/2 times the sine of 2 theta. Now notice here, I'm not doing the additional simplification for the sine of 2 theta. Because here, all I need to do is fill in my limits, my new limits of integration, and I'll be able to get the answer. I don't have to worry about having my picture where we only have the theta in the triangle. So now I have my new limits of integration, and I'm sorry, that should be a theta there. I'm sorry about that. So then I just fill in my results. So I have 9/4 times my top limit is pi over 6 plus, what is this, 9/8. Now this is going to be the sine of 2 times pi over 6, which is pi over 3, right? And that pi over 3 is 60 degrees. So the sine of 60 degrees from our picture here is the square root of 3 over 2, right? 60 degrees here, 60 degrees. The sine is square root of 3 over 2. So this here can be replaced by the square root of 3 over 2. And then it's minus, and it's going to be all zeros. Then I replace the 0 for my theta. Well, that gives me a 0 for my first term. My second term is going to be the sine of 2 times 0, which is 0. So I'm going to have a 0 there also. So with my definite integral, I can keep it all in theta, and then I get whatever this simplifies to. I think the first thing is 3/8. 3 over 2, 3/8 plus 9/8 times the square root of 3 over 2, like that. Okay. So I don't have to go all the way back to x again. I just have to change my thetas and work with the theta. All right. Why don't we take about no more than a 5-minute break, and we'll continue on with this. Exactly 11. I've heard about it. As long as you understand it, you can use it. I think you can only use it if this is a polynomial. Yes, that's yes. And if you want to go on and use this, I mean, that works very nicely for this. This is an easy one because this is just e to the z always stays the same. Yeah, that's fine, as long as you understand it and show your work. Yeah. It's something like it's called the tabulated method or the table method of integration by parts. But one of them has to be a polynomial.
I know, I did it with sine.
It would work with sine times a polynomial. Yeah, right. It'll work with that. Right. Missed you on the other day. Huh? Oh, yeah. And the last two recordings have failed on this crazy thing. Fridays didn't work at all. And I think Monday I stopped it too quickly because of that other class coming in, so the Monday recording didn't work. But I have all the scanned notes. Yeah. But you know what your best resource is, of course? Is this thing right here. This is your best resource. Am I right?
The homework book.
The homework book, right. You have it on Kindle, so that it's not as heavy. Did you know this thing is that you can get the book on Kindle? So you can always have it with you? Oh, you have it on your laptop also. But you had it paid on. Okay, all right. It was nothing, not quite kosher.
I
And
had
the same thing again.
mine on my website with the PDF. No.
How did you say for it?
Passed around for quite some time. Ever since I accidentally put it on Blackboard.
Somebody posted it at some point in time, the PDF for free.
Yeah, it's on
Yeah,
Blackboard.
you can get it all of them. I didn't get one off the internet. Mine came off the student directory at Merrimack, so.
They have it on the student directory in Merrimack.
They did, yeah.
So it's on an official
It has to be
site.
on one of those, no, you have to be on one of the computers at Merrimack.
And there still, it's an
Yeah.
official Merrimack computer. They've got the PDF where you don't have to pay for it. That's not, well, I guess you pay for it by being a student at Merrimack.
They got rid of that.
Sure. The book. Oh, apparently, everybody knows about it except me and you. That you can get it for free. You have the PDF somewhere.
Actually, have it on my phone.
I've seen people with iPads. They have it on their iPad. Yeah, I have it on my iPad, but since I didn't know about the freebie, I paid $180 for it. You paid more than that. About 188, you mean?
I don't remember what I paid.
If you paid more than 188, something happened that's wrong. I mean, yeah. Wow, that's interesting.
I didn't say.
Well, now I know. But I can't exactly, like at the beginning of the semester, go on and publicly tell students to go on and get a copy of it off the internet. Maybe I can say, I've heard a rumor. A rumor that it's on the internet. I don't know. Okay, we need to get started again here. All right. A couple more examples in this section here. And I know I seem to be emphasizing the sign, but anyway, that's the way it is here. Okay, here's an example. du over u times 5 minus u squared. Okay, so we're just changing the variable to a u. Now, since the variable is after the minus sign, we're going to use the sign of theta. All right. Now, what's our a going to be here? Remember, if the normal thing is square root of a squared minus u squared or x squared. So it's going to be the square root of 5 because here we have a 5. So a squared is equal to 5. So the a that we're going to use is the square root of 5. So our substitution then is going to be x equals the square root of 5 times the sine of theta. All right. Oh, you're right. Thank you. I'm so used to x. U equals that. So du, of course, is the square root of 5 times the cosine of theta, d theta. And let's see. Our radical 5 minus u squared is going to be replaced by 5 minus, let's see, u squared is going to be square root of 5 times square root of 5 is 5 sine squared of theta. And so I can take out a 5, but that means I have to put a square root of 5 in the front. Square root of 5 times 1 minus the sine squared of theta. And of course, that's going to turn out to be the cosine. So square root of 5 times the cosine of theta. All right, so let's replace everything now. Our du is going to be replaced by the square root of 5, cosine theta, d theta. Now don't forget here, we have a u here in front of the radical, so I need to stick that in here. So my u is square root of 5 sine theta times, and then I'm going to replace the radical with the square root of 5 times the cosine of theta. All right, so get everything replaced. Cancel out what we can cancel out. Looks like a cosine can be canceled out. It looks like one of the square roots of 5 can be canceled out. So let's write it again. We still have a square root of 5 in the denominator, and we still have a sine of theta in the denominator. Okay. Now, remember the 1 over the sine is the same as the cosecant. So this is the integral of 1 over 5 times the cosecant of theta, d theta. All right. I think here I'm going to show you how we derived this formula for the antiderivative. It's a clever little multiplication of top and bottom. So bear with me for this. What I'm going to do here is this is, of course, over the denominator of 1. I'm going to we have the cosecant of theta. I'm going to multiply the top by the cosecant of theta minus the cotangent of theta. But if I do that to the top, I also need to put that in the denominator. So the denominator is then cosecant of theta minus the cotangent of theta, d theta. All right. So let's see why this clever little multiplication on top and bottom, which if I'm seeing a wrinkled brow over, might be helpful. All right? Let's distribute this on the top. So we have cosecant squared of theta, then we have a minus, and then we have the cosecant times the cotangent. Cosecant of theta times the cotangent of theta, d theta, all over, and then our denominator is the cosecant of theta minus the cotangent of theta. So this is works out very nicely here. We can do a u substitution here, and it'll work out. Let u equal our denominator. Let u equal the cosecant of theta minus the cotangent of theta. And let's get the du, the derivative. Well, the derivative of the cosecant, let's see, the derivative of the secant is the secant. The derivative of the cosecant is the minus cosecant cotangent. So minus cosecant cotangent. Now the derivative of the tangent is the secant squared, but the derivative of the cotangent is the minus cosecant squared. And notice we have a minus in front. So this will be plus the cosecant squared of theta d theta. Now let's compare the du that we got with this new numerator that we obtained because of the multiplication. This numerator is the same, cosecant squared minus cosecant cotangent is the same as our du that we just have obtained. So I can do a u substitution now with this, and this whole mess becomes 1 over u du. Do the natural log. Equals 1 over the square root of 5 times the natural log of the absolute value of u plus our c. So this is going to be 1 over the square root of 5 times the natural log of this whole u here, cosecant of theta minus the cotangent of theta, plus our capital C. So I want you guys to try to internalize this formula if you can. So let me put an asterisk here by this formula. I've done this already, but so the bottom line here is the antiderivative of the cosecant is the natural log of the cosecant minus the cotangent plus C. All right. Okay. Okay, so we obtained our antiderivative here in terms of the theta, like we've done before. So we need to get x back in our answer. All right. So again, we're going to draw a picture. We're going to stick in our theta here. Now let's go up here, way up here, and we had, actually, I'm sorry, I should say get the u back, because we started with u. Get u back. So our initial substitution was u is equal to the square root of 5 times the sine of theta. All right. So divide by the square root of 5. So we have u divided by the square root of 5 is equal to the sine of theta. And we can use that to fill in our triangle here. So the sine is going to be opposite u hypotenuse square root of 5. And then the remaining leg is going to be the square root of, well, the square of this is going to be just 5 minus the u squared. All right. Which is the formula that we see in our integral. All right. So let's see here. Let me get our answer back here. So this is our answer in terms of theta. So we're going to go 1 over the square root of 5 times the natural log. Now the first thing we need is the cosecant of theta, which is the reciprocal of the sine. So that's going to be square root of 5 over u. Just read it right off the picture. Minus, and then we look at the cotangent, which is the cotangent. It's the adjacent over the opposite. So that the adjacent here is square root of 5 minus u squared over the opposite, which is the u. And close the absolute value, plus c. And then that's our antiderivative. Okay? So you can see the process is all the same. Do your substitution using those tables. Get everything in terms of theta. Simplify what you can. Draw your picture and get your antiderivative and draw your picture. Okay, there's one other one then I want to do here in this section. And that is this one. This one's a little bit different. Saving the best for last here. Okay, here we have the integral of 5 plus 4x minus x squared, all under the radical dx. and you look at that and say, how in the world can I apply this section to that integral? All right. Well, let's initially rewrite this a little bit. Integral of 5, keep the 5 in front, put a minus sign here, and then notice we have a minus x squared. So if I'm going to, in the parentheses here, I'm going to put a positive x squared because I have a minus in front. And now here I have a plus 4x. So in order to keep it the same expression in the parentheses, I need to make this a minus 4x. So we've got it tentatively written as some number minus something. All right? But if we want to use these tables here, I've got to end up with something like, in this case, something like this, the square root of a squared minus u squared, all right? So what we have here, we have 5 minus, what I want to do here is complete the square inside the parentheses in order to give me a square. So good old college algebra, completing the square, is rearing its ugly head, perhaps, depending on how you feel about that. So I want to complete the square inside the parentheses, but I want to be careful not to change what is the actual total expression under the parentheses. So I'll say this, without changing the expression under the radical. Because if I change it, I change my problem. All right. So let's look at completing the square for x squared minus the 4x. Okay, with completing the square, what do we do? Do we remember what we do? Okay, well, this is what we do. We take the coefficient of the x term and divide it by 2. So that gives me a negative 2. And do we know what we do with that? And we square it. Square the result. Now be careful, this is negative 2 in parentheses that I'm squaring, and I get a positive 4. All right. So therefore, plus 4, x squared minus 4x plus 4 is my perfect, it's a perfect square trinomial, perfect square. In fact, what is it? What is it's going to be something times something. What would be in the parentheses here? X minus 2. All right. The minus 2 here is what I get, is actually the number I get when I divide that coefficient by 2. That is going to be the number that's going to be inside the parentheses. Okay, so the thing is, so in this process, I added a 4 inside those parentheses. So let's go up here from our original expression that we got here. So I have 5, and I'm going to leave a space here, minus, and now in the parentheses, we're going to have x squared minus 4x, which we already had, but we're now going to have a plus 4, because we used the plus 4 to complete the square. Now, what has that done then inside, underneath this radical? It has subtracted a 4, right? Minus a 4. If I minus a 4 now, I have to add that 4 on under the radical. So I have to compensate for that change by adding a 4 there by the 5. Otherwise, I'm changing the expression under the radical. So my new expression here becomes, let's see, integral of 5 and 4 is 9 minus, and then in the parentheses, I'm going to have x minus 2 squared dx. So in this case, I had to do some work in order to get it in this form here, the square root of a squared minus u squared, right? And this could also work with, it could have worked the other way around, where I could have had the x squared in front, where it's u squared minus a squared. It could have worked that way also. Okay, now, I'm going to use a sign because the variable is after the minus sign. Variable after the minus. So I'm going to use a sign. What's my a here? A is 3 because a squared is the 9, so my a is 3. So the substitution that I'm going to use here, now this whole thing then, x minus 2, that's going to equal 3 times the sine of theta. That whole thing that's being squared there, I'm going to take that expression, x minus 2, and set it equal now to my 3 sine of theta. Okay. Before we go on, we ended up doing some manipulation to have under the radical, something squared minus something squared, and then we know we have to use a sign. So instead of just plain old u or x here on the left, we have to use the expression here that we're squaring. We're going to use the x minus 2. And that's going to be the 3 sine of theta. So this is our basic substitution here. All right. Once you've got that under control, the rest of it's fairly straightforward. Okay, so let's see. Let me write this again. X minus 2 is 3 sine of theta. So let's get our dx. So dx, well, this minus 2 is just going to go to a 0, right, when I do the derivative. So dx is equal to 3 cosine of theta, d theta, all right? And our radical here is radical is square root of 9 minus x minus 2 squared. That's going to be changed by the square root of 9 minus, now x minus 2 here is equal to 3 sine of theta. So when we square it, we're going to get 9 sine squared of theta. Okay, we just square it. And then we can take the 9 out from the radical and make it a 3 in front. 3 times 1 minus sine squared of theta. And then that's equal to the cosine squared, the square root of the cosine squared. So I end up getting 3 cosine of theta as my radical expression. Okay. So let's replace what we have, our integral, with the theta. So therefore we have it's our radical is going to be 3 cosine of theta. And then our dx here times 3 cosine of theta d theta. All right, just replacing things. Let's simplify this. We get a 3 times 3 is a 9. 9 cosine times cosine. We have a 9 cosine squared d theta. All right. All right. So we have a cosine squared. So we're going to use that nice little formula because we want to get the antiderivative here. The cosine squared can be replaced by 1/2 times 1 plus the cosine of 2 times theta. Okay. So we're now going to have 9 times 1/2 times 1 plus the cosine of 2 theta d theta, and we'll be able to get that antiderivative. Let's separate it out here a little bit. 9 over 2 times 1 is 9 over 2 d theta plus 9 over 2 times the cosine of 2 theta d theta. Separate it out into 2, and we can get these antiderivatives. 9/2 times my variable theta, 9 over 2 times theta, plus, and again, this we're going to do our nice shortcut. This is going to be 9 over 2 times 1 over 2, because we have a 2 here. So this is going to be replaced by 9 over 4. And then let's see, the antiderivative of the cosine is the sine of 2 theta, plus our c. Okay. So we've been able to get the antiderivative in terms of theta, and now we get x back. Ooh, we're still going to have a problem though, aren't we? Because notice here, we have the sine of 2 theta. So let's take care of that. Well, let's draw our picture first. That's fine. Here's our right triangle. Here's our theta. Now, let's remember what our substitution was originally. X minus 2 equals 3 times the sine of theta. That was our original substitution. So let me divide by 3. So we get sine theta is equal to x minus 2 all divided by 3. All right, so I can fill in 2 of the legs right away. The opposite leg is going to be x minus 2. The hypotenuse is going to be 3. Now, the remaining leg is going to be 9 minus the square of x minus 2. Okay. And notice that this is also, because is also our original radical 5 plus 4x minus x squared. Okay. When we completed the square, we did not change ultimately what the expression was under the radical. We subtracted by a number and we added by the same number. So either one of those radicals has the same basic expression underneath it. Okay. Now the thing is, again, as we've seen before, our triangle has a theta in it, but one of our antiderivatives has a sine of 2 theta, so we have to change that. So this is 9 over 2 times theta plus, now the sine of 2 theta is 2 times the sin cos, 2 sine theta cos theta. So this is going to be 9 over 4 times 2, which is 9 over 2, sine of theta cosine of theta plus c. So now everything's in terms of theta. All right. Now, theta here is going to be replaced. Well, let's see. Sine of theta is x minus 2 over 3. So theta is the sine inverse of the x minus 2 over 3. Then plus 9 over 2. And then the sine of theta, let's see. Sine of theta is x minus 2 over 3 times. And then the cosine of theta is, let's see, adjacent over the hypotenuse, so that's going to be the square root of 9 minus x minus 2 squared, all over my hypotenuse again of 3. All right. And then plus c. And again, I can do some arithmetic simplifying of this. 3 into 3 goes 9. I can cancel out these numbers here if I like. Okay. You will have a problem in your homework of this business where you have to end up completing the square in order to evaluate the antiderivative using these tables. I will admit these sections are challenging, and so this might even be one of the most challenging parts of the course. It's just this integration. Integrals are not easy. They require some trial and error and stick-to-itness, and not just giving up and throwing up your hands and saying, I can't do it. But they are not easy. We're not stopping yet. I want to...
What's the question on test or something, right?
Well, I haven't made up the test yet, so I'm very well aware of time-consuming, so I'm not going to be having you to do 20 integrals in 90 minutes or something like that. So anyway, I'll figure it out. But I want to move on to this next section here. And there was something really interesting, though, I want to say that in Stewart that I read. Figuring out integrals, there's really only two tools that we have. We've talked about all this stuff. There's really only two tools that we have for integrals. Integration by parts and substitution, some kind of substitution. That's it. Those are the two tools that we have to use. Parts or substitution of some kind. All right, this next section, 7.4, I want to get just a start on this. This is where we are integrating polynomials divided by polynomials. Integrating polynomials divided by polynomials. Now, there's a fancy expression for a polynomial divided by a polynomial, and it's called a rational expression. The way that we're going to do this is by using what is called partial fractions. That's going to be our tool. And what we do with partial fractions is this. We rewrite our original rational expression as a sum of simpler fractions, and that's the key word right there, simpler fractions, and we can integrate those fractions, those simpler fractions that we can integrate. All right, that's the basic process here with this. So let me show you something in the reverse direction from algebra. Let's look at 2 divided by x minus 1 minus 1 divided by x plus 2. And what I want to do is combine that into a single expression with a single numerator expression and a single denominator expression. And we know that the way to do that is to get a common denominator. Our common denominator is going to be the x minus 1 in parentheses times the x plus 2, a common denominator. So this first fraction here will rewrite as, okay, I've got my new denominator of x minus 1 times x plus 2. But so what do I have to do to this numerator here if I'm multiplying the denominator by x plus 2 to get a same expression? Okay, by the...
Like, you multiply the 2 by x.
Yeah, to multiply the 2 by what I had multiplied the bottom part by. Okay? Otherwise, I'm going to have a different expression. And then minus, And now this one here, I want to also have it be the common denominator of x minus 1 times x plus 2. So this one here, this 1, I'm going to have to, it originally has an x plus 2 in the denominator. I need to multiply it by the additional factor of x minus 1 in order to get equivalent expression. So I now have two fraction expressions with the same denominator, so I can combine them into a single expression, and then all I do is distribute and get my top expression here. So this is going to simplify as 2x plus 4 for distributing the first one, minus x, and then a double minus plus 1. So what does that simplify to? Combined terms, I get 2x minus x is x, 4 plus 1 is 5, so my numerator is x plus 5, and my denominator is x minus 1 times x plus 2. All right. Now what we're going to be doing here in this section is going the other direction. And by the way, this boils to x squared plus x minus 2. So this is what we will do is the opposite. Is the opposite direction. You're going to start with an integral like this. The integral of x plus 5 over x squared plus x minus 2 dx. And you'll be asked to evaluate this. The key here is that we're going to break it up into, we know that this expression here, if we go in the reverse direction, this is equal to the integral of 2 over x minus 1 minus 1 over x plus 2 dx. Just going in the opposite direction. And we can definitely integrate both of those individual expressions. By using the natural log, this is going to be 2 times the natural log of x minus 1 minus the natural log of the absolute value of x plus 2. Two easy integrals plus our c. All right. But offhand, just looking at this right here, if you try a u substitution offhand, you're going to have some difficulty, all right? So what we do is we replace it with two easier fractions. Yeah?
Okay, say we're just given x plus 5 over that at the beginning. How do we get to over x minus 1? How do we do that?
Well, did I tell you to ask that question? I did, didn't I? Because that's exactly what we're going to be doing now. Okay, learning how we go from, say, that to the other thing. Okay, that's what we're going to be learning. All right, let's see how far we can get with this. Okay, we can do this process. Let me just write this back down. We can do this partial fraction process if, big if the degree of the top polynomial is less than the degree of the bottom polynomial. If the degree of the top is strictly less than the degree of the bottom. Now, let's refresh ourselves, make sure we understand what we mean by the degree of a polynomial. It's the biggest exponent in the polynomial. So let's go back to this example here. This top one here, our biggest exponent is a 1, x to the first. So this top one has degree equal to 1. The bottom one, our biggest exponent, is a 2. So it has degree equal to 2. So we can break this up using the partial fraction technique that we're going to learn because we initially have the degree of the top is less than the degree of the bottom. All right? We have time for me just to get a start on this process. Let's look at this. I'm not going to put the integral in here yet. I'm just going to put the expression. Okay, on the top, we have x squared plus 2x minus 1. And on the bottom, we have 2x to the third plus 3x squared minus 2x. Ooh, okay. Now, and we want to represent this as something plus something, however many we need. And we'll find out how many we need. All right, the first thing you have to do here, first of all, we notice that the degree of the top is less than the degree of the bottom, okay? Degree of top is smaller. You want to make note of that. Okay. Now, we have to fully factor the denominator. Now, I'm going to tell you guys this, that probably on the exam, I'm probably going to give you the denominators already fully factored, okay? But in this case, we have to fully factor the denominator. Now, in this case, that denominator, let's see how, there's an x that I can take out of each term. So it's x times 2x squared plus 3x minus 2. All right, and then by trial and error, I can then factor what's in the parentheses. So I still have my x, and this factors as, the parentheses factors as 2x minus 1 times x plus 2. And you can check that out, that does FOIL out. So we have to fully factor the denominator if it is not already presented to us as fully factored. All right. Then what we do is this. We have 1, 2, 3 factors. In fact, in this case, there are 3 different factors. All right. So up here, we put the first factor in the denominator for my first expression. We put the second factor in the denominator for my second expression. And we put my third factor under that, in that denominator. All right. By the way, these are called linear factors because they only have a power of x of 1. They're linear factors. Power of x equals 1. All right. Then what in the world do I put up in the numerator? Well, right now I don't know. So what I have to do is solve. I'm going to have to put some variables up here. I'm going to put the variable a for the first one, the variable b. I'm not a variable. We're solving for it. The number b up here and the number c for the third one. And the next thing we have to do is then solve for a, b, and c. Okay. Well, how in the world do I even start to do that? Okay, we have a couple minutes. Let's write this. Let's go down. Let's take what we had here, and I'm going to write it like this: x squared plus 2x minus 1. And I'm going to write my denominator here in the fully factored form over x times 2x minus 1 times x plus 2. And that's equal to some unknown a over x plus some unknown b over 2x minus 1 plus some unknown c over my third factor. All right. So we've got a whole bunch of denominators here, and what I tell my algebra class is, I hate denominators, I want to get rid of them. So what we have to, and this is an equation, so what we have to do to both sides of this equation is multiply by all these factors on both sides. In other words, I multiply everything by this expression here, x times 2x minus 1 times x plus 2. Multiply both sides. Don't forget one side, by x times 2x minus 1 times x plus 2. And that'll get rid of my denominators. So now what we're going to have, and this is where we're going to leave it here, now what we're going to have, on the left side, we will no longer have a denominator, we'll just have x squared plus 2x minus 1 equals. Now, remember, we're multiplying every single one of these by this expression. So here I have a over x, and I'm multiplying it by x times 2x minus 1 times x plus 2. Well, what's going to cancel out here? The x's are going to cancel out, and I'll no longer have a denominator. Then I have my second expression, b over 2x minus 1. Again, that is being multiplied by x times 2x minus 1 times x plus 2. And again, this 2x minus 1 will cancel out of both top and bottom. And then I have my third one, c over x plus 2. Again, going to be multiplied by x, 2x minus 1 times x plus 2. And again, we'll get rid of our denominator because we can cancel out an x plus 2. So the last thing I'm going to write is this. This is what we're going to end up with. Our expression on the left, just the numerator part of it, and that's going to equal the following. A times 2x minus 1 times x plus 2 plus b times x plus 2 plus c times x times 2x minus 1. So we have an equation now where we no longer have denominators. And we're going to see a very clever way that I think that there is to solve for A, B, and C when we start up again on Friday. Very quick way to solve for the A, B, and C once we've gotten it this far. Okay. Thank you.
Will you post the homework for 7.3 before Friday?
It's a big, I actually just finished the homework assignment, and that'll be due, well, wait a minute, 7.3, yeah, that's going to be due a week from Friday. I can get it posted. Yeah, okay. Look later today. Okay. Yeah. Oh, yeah, I hear you. I hear you. I'll get it posted.
Is there a class in here?
No, only on Monday do they barge in. What's that? Oh, it's not till, right now it's scheduled for October the 4th, but that's a Friday. I'm probably going to move it back like I did the other ones to the Wednesday. Yeah, it should be October the 1st. Yeah. Or 2nd or something. October